Hey everyone, here we are, we're live. So just finished Codeforces Educational Round 101 for Div 2. As Prasad, please don't paste code into the chat. Anyway, so just finished the contest. Only 6 problems this time, and I thought it was some pretty fun problems. I actually thought B was the easiest problem. I thought A was a little bit tricky. There are a couple of things you have to kind of figure out or prove there if you haven't seen that type of thing before. I guess if you have seen it, it's a little easier. And then I thought C was kind of hard, and I thought D was pretty hard as well. So yeah, you can kind of see that's reflected in the solve counts. Pretty big jump from B to C in difficulty. Although a lot of people got D. I'm a little surprised by that actually. Maybe there's something easier than what I did. I'm not sure. And then yeah, like as kind of you'd expect, decently big jumps from D to E and then from E to F in difficulty. Yeah, it looks like at least a lot of like solves for the early problems, which is good. You don't want to have contests where like even the first 1 or 2 problems are way too hard. In terms of results, let me see, this is updated. Yeah, so I got tied for second, so I guess 2.5 is my placing with geothermal, and then yeah, Janley was super fast, 42 minutes, so good stuff there. And oh, this is friends sittings, right? And yeah, a lot of people solved everything, but let me see how many actually. Oh, that's actually a lot of people. Okay, so 66 people got all 6 of them, at least for now. We'll see after hacking and everything. But cool. So, oh, and D worked with special numbers. I see, yeah. Kaklosi said you solved A faster than me. Yeah, I guess you got it in 1 minute, I got it in 2 minutes. So, nice. Okay, so we can just go through some of these problems here. Oh, we got a hydrate, and actually we did have an earlier hydrate, so I guess I will do 2 hydrates. Okay, so yeah, first we'll do problem A. We'll talk about this one. So in problem A, you have a bracket sequence, and they define what it means to have a regular bracket sequence. This is actually a super like common topic that comes up a lot, so it's worth just like getting familiar with this if you if you plan to do more contests. Basically, it's a sequence where where you can like make a mathematical expression using it. And so what that means is like all of the parentheses have to be matched. So these are matched, and then this one matches with this one. I can make this a little bigger. Okay, this first one matches with the fourth one, and so on. And then the other thing is that when you have matches, like it's always a left paren matching a right paren, and not the other way around. And so a couple examples that are bad are right paren, left paren is bad. This is bad because they're not all matched, and same for this. No, sorry, this one is, yeah. This right paren doesn't match any left paren. And so now we're given a sequence of characters, left paren, right paren, and question mark. And yeah, there's exactly one left paren, there's exactly one right paren. And otherwise, we need to replace every question mark with either right paren or left paren. And we want to determine if we can obtain an RBS. So basically, this problem, there's some like background you need to know. to make it easier to solve. So first of all, one really obvious thing you can do is n has to be even, or else it's not possible. Any balanced, this is also called balanced sequence, and it's also called a regular bracket sequence. So anything that's odd cannot possibly be regular. So we can just print no. And then otherwise there's a greedy idea, which is when we have question marks, we're going to replace half of them with left paren and half of them with right paren. And then the first half will be left paren and the second half will be right paren. And this idea, it's basically what I was describing earlier, where you want to match a left paren on the left side to a right paren on the right side, and not the other way around. And so, because of this 1 and 1 setup, the remaining question marks will have to be split up half and half. And the best way to split them up is left parens and then right parens. So for kind of a more formalized way of thinking about it, the way I often think about these sequences is that we're just kind of building these diagrams. I think there is a name for this diagram. I'm not remembering it off the top of my head. But basically a left paren, it means go up 1. So 2 left parens means go up 1, go up 1. Right paren means go down 1, and then so on. Left paren, right paren, right, right. And so a regular sequence starts at 0 and ends at 0. And then the important thing is it never drops below 0 in the middle. So it can touch 0, but it can't drop below 0. And so if you look at a bad sequence like this one, we have left paren, right paren, left paren. The reason it's bad is because we do drop below 0 here. And then if you want to be formal about it, you can prove that if you have a right paren here, some stuff in the middle, and a left paren here, it's better to swap them. Because basically what you're doing is, I'll just go over this real quick. Basically what you're doing is you have this part where you go down, you have something in the middle, like this part, and then you go up, and instead you're just replacing that with going up, doing the middle part, and then going down. And so this is always better because it has the same end result as the beginning. And you're just kind of shifting this part from here to here up by 2. And so it's always better to have left parens on the left and right parens on the right. So yeah, so we just implement this as a greedy. And yeah, basically I just go through the string, find the question marks, check the index, compare it to this number, which is the half of the question marks. And then if it's on the left side, I'll make it left paren, otherwise right paren. And then I just check if the result is regular and print the answer. Checking the result is just this kind of level thing that we're talking about. So if it's a left paren, level plus plus, otherwise level minus minus, we just make sure we never go negative, and then we make sure we end up at 0. Yeah, so people are saying my idea is overcomplicated. So yeah, so basically my idea can solve something more general than this. Like it can solve any string with any amount of left parens, any amount of right parens, and any amount of question marks. You just make sure that you end up with the right number of each. Probably there's an easier way to do it, given that it's just one of these and one of these. I actually didn't end up thinking about that. So maybe that's why it took me 2 minutes instead of like 1 minute, like the rest of you guys. Yeah, there's probably something simpler, like as long as the right paren isn't the first and the left paren isn't the last, or something like that. I bet there's like a couple cases that you can do in this particular problem. Yeah, you can cheese this from Showu. Yeah, pretty much. Okay, but anyway, yeah, that's the more general idea. So either way, it works. And so yeah, we'll just move on to B in that case. Yeah, okay, so for problem B, we've got a sequence of n plus m integers. There are 2 colors, red and blue, and n of them are painted red, and m of them are painted blue. And then after that, you kind of pull out 2 sequences, which are the red numbers and the blue numbers, in the same order that they originally appeared. And Keklux asks, will I stream Goodbye Contest? Not sure yet. I would say probably not, given that I'm streaming today, but it's possible. We'll see. I'm not even sure if I'll enter yet. But anyway, okay. So back to this. The original sequence is lost, and we only have R and B. And we want to build the original sequence A, but we want to choose the way that maximizes the value of this function, which is the max of 0, A1, A1 plus A2, A1 plus A2 plus A3, and so on, up to the sum of the entire thing. And we want to compute the maximum value of f of A. So this list, basically, if you aren't familiar with this yet, this is just all of the prefix sums of A. This is a pretty common idea in competitive programming where, let's say you wanted to compute like sums of subarrays. So you wanted to compute like the sum of AX plus 1 all the way through AY. You could compute this array, and then any subarray would just be like one value in here, one prefix minus another prefix. So this is a very common idea. And so yeah, we're just maximizing, in this case, we're just maximizing the max prefix of A. Yeah, I removed IRL word ban for now for the post contest streams because it's doing a lot of analysis. But I'll keep it back in for more chill streams later. Okay, so yeah, so we have this red sequence and we have this blue sequence. And then what's going to happen is we're just going to kind of interleave them in some order. We'll just take like different elements and like do something like that, right? And so if we have, let's just take one example. We can do something like this. And we can set A to be that, right? And then what we'll notice is if we look at like any prefix of this A, basically, for example, this one, we'll notice the sum is R1 plus R2 plus R3 plus B1 plus B2, right? So we're actually getting a prefix of R and a prefix of B. And this makes sense. Definitely any prefix of A will be a prefix of R and a prefix of B. And then it also turns out that like if we have any combination of like some prefix of R and some prefix of B, we can set up a sequence A that does end up with that prefix. One really obvious way is like, let's say we want R1, R2, and we want B1, B2, B3. We can literally just do R1, R2, and then B1, B2, B3, and then just finish it. And then this will be a prefix of A, right? So pretty much we just want the max possible value of some prefix from R plus some prefix from B. And so we can just write the code really simply to just do that. Read in R, read in B, take all of the prefix sums of R here, take all the prefix sums of B here, and then take the max sum from R and the max sum from B and add those together. Got a hydrate. So let's see. Nsky Bitsky asks why not using partial sum? So yeah, I think C++ has something like this. How does this work? Oh, I see. Yeah, so this I like never use this. I think the main reason there are two main reasons, I guess. I have seen this before, but I've kind of forgotten about it. But basically, the first reason is like this is super easy. It's just a really basic for loop, so it's not really a big deal, as opposed to something like sort in C++, which is really nice to use, because that would actually be a lot of code otherwise. And the other thing is this doesn't include 0, and that is pretty important to make sure you include 0. In general, for partial sums or prefix sums, same thing. You want to include 0 so that you can get like prefixes of the array as well. when you subtract something and 0. And in this case, we also did include 0, so we want to make sure that's an option. Yeah, so you can just call it partial sum with the iterator after the begin, so you can have a 0, but at that point, I don't know, it just seems a little annoying to me. Like, it seems like this is just easier. Also, another thing is that, like, what happens if you have an array of ints and you want a sum array of int 64s? Does it handle that properly? Like, there's a lot of details here where I just am in the habit of writing this loop instead because I know this works and it's super easy. Yeah, there definitely exists a solution better than m times n, Malvika Bila asked. You just take the max sum from R and the max sum from B, and you just add them together independently. And so this is just n plus m. Yeah, but it's nice that they didn't require that because it's not really, well, it feels like it's not like necessary to make this problem just like huge n and m and just have like a ton of input. We have some conflicting requests. So a lot of people are saying Kadan. I'm not sure what you're suggesting here. Like, are you asking about are you taking the largest subarray from each? Because you can't do that. You can only take prefixes. So that's why we only do prefixes here. Okay, if someone missed the if anyone missed the explanations for A and B, by the way, we just covered those. So I linked the videos for this current stream. You can even find the current stream in there and you can replay parts. So that way you can just check that out. And one thing I'll just mention really quick before going to C is, yeah, so you can follow my channel to get notified when I do future streams. It'll just give you a notification whenever that happens. So if you want to check out future streams, just give me a follow. Okay, so can I quickly cover the last stream? Okay, yeah, so for problem C, so this one had a big jump in difficulty from B. It looked like A and B were pretty similar. And for this one, yeah, actually, the first read through this, I had to I didn't know what to do. I had to think about it for a little while and then figured it out. So basically you have a fence, it's gonna have n equal sections. We'll get a hydrate. Every section has a width of 1 and a height of k. So it's these blue rectangles, they're all the same size. And we're gonna place them in a line side by side. But the ground underneath the fence is not flat. And they tell you that, I don't know why they say for simplicity, but basically the ith section has a height of hi. I guess they're like modeling a smooth curve as like a histogram instead. And we have several rules that we need in order to build this fence. So first of all, the sections next to each other, consecutive sections, have to have some common touching section, side length of at least 1. And also the first and last sections should be exactly on their ground level. So the first section here and the last section here are exactly on the ground level and not hanging up in the air. And lastly, the sections can be on the ground level or higher, but they can't be higher than k minus 1 from the ground level. And so this one is an example where k is 3, and so each of these is 3. And so this one, and this one, the second, third, and fifth sections are all 2 above the ground level. And then basically these two sections overlap by 1, which is fine. These two overlap by 1, which is fine. these two sections overlap by 2, which is also fine, and so on. And so this satisfies all the conditions. And then we just need to figure out, given n and k and the hi, is it possible to build a fence that satisfies everything? Yeah, so basically the way to go about solving this is start from the statement and think about it and just make a couple observations. So first of all, we can say that, let's say that every fence section is placed at xi. So what we know then is that from rule 3, we know that hi is less than or equal to xi, which is less than or equal to hi plus k minus 1. Yeah, and basically you can show that xi has to be an integer, but anyway, we can just start with this. Or not has to be an integer, but we can just assume that it will be an integer. So rule 3 tells us this assumption, or this requirement. And then rule 2 tells us x0 is going to be equal to h0. Or I guess I should go for, I'll just use the same one-base indexing for the problem because it makes this easier. Xn is equal to hn. So that's requirements here. Xi, I'll just write it here, equals the height of the bottom of fence section I. This is from rule 3. This is rule 2. And then rule 1 tells us consecutive sections should have a common side length of at least 1. Okay, so what that really means is that basically xi minus xi plus 1, the absolute value of the difference is at most k minus 1. And that's just because if you think about these two consecutive sections, the second one can be at most 1 away from the top, which is xi plus k minus 1. And then the same in the other direction for the same reason. So it's just absolute value of the difference is at most k minus 1. And we just want to know if we can find an array xi that satisfies all these conditions. So basically, the key thing is that if it weren't for this rule, so this is rule 1. If it weren't for rule 1, it would be very easy to do, right? We just set this to this, we set this to this, and we have so many choices here. The only thing that actually makes it hard is rule 1. And rule 1 only involves consecutive things. So basically we can just kind of go from left to right, and we can track, if we think about tracking okay, for what are the possible choices for x1? Well, there's only h1, right? And then based on that, we could figure out, okay, what are the possible choices for x2? For x2, it has to be between h2 and h2 plus k minus 1. And then it also has to satisfy this. And so we get a couple different inequalities. So basically, if we take this and we write this as let's just write it that way, then first we have this from rule 3. And then we also have, because of this above, we have xi. First of all, it's got to be greater than or equal to xi minus 1 minus k minus 1. And it's also got to be less than or equal to xi minus 1 plus k minus 1. So both of these constraints have to be satisfied at the same time. So we just have two ranges that we need to be in both of at the same time. So we're just doing intersections of ranges. And so that gives us still a range, right? The intersection of two ranges is still a range. For example, if you intersect 4, 8 with 5, 10, you'll end up with 5, 8, right? And because of that, we can just go from left to right. Go to hydrate. You can just go from left to right, starting from 1, going up all the way up to n. and just track the ranges of what xi can be. So basically, we just read in the input, and then we start with a range. So I'm using a half open range here. So basically, instead of 4, 8, which means that 4, 5, 6, 7, 8 are all good, I'm using the range 4, 9, which means that 4 is good, but 9 is not good. So it's still the same range overall. So yeah, so basically for 0, only H0 is allowed. And so that's why we have this range. And then when we go from, I minus 1 to I, basically we subtract k minus 1 from both ends because of this requirement. And then we have a second requirement, which is that we have to be between hi and hi plus k minus 1, or since we're doing half open, plus k. And then finally, we just intersect these two ranges together, and that's our new range for I. And intersect is just max of the two lower bounds and min of the two upper bounds. And if at any point our range becomes empty, then we just break out. And we go all the way up to the last one. And then all we have to check is that because we've already handled this, we've already handled this, and we've already handled this, we just need to check this last one. And so as long as the last value of h is between our range 0 and range 1, then the answer is yes. And otherwise it's no. PBO5, you can check out the replay of the stream if there was something that was confusing. So why did I go with an open segment instead of a closed segment? Yeah, so I just generally like to use half open ranges. Half open ranges are really nice because a couple of different reasons. One is that, for example, if you're just taking the range of an array, it's just 0 to n instead of like this 0 n minus 1 stuff. And then the other thing is, if you want to know if two ranges are exactly touching, they just look like this. For example, 4, 7, and then 7, 9, right? Those ranges are exactly covering 4 through, like they combine to make 4, 9, right? Whereas if you wrote it this way, it would look like this, which is a little weirder. Another thing is like A to B half open, the length is just B minus A as opposed to like B minus A plus 1. So there's just a lot of things where half open ends up being a lot more convenient and easy to work with. Yeah, so actually when I thought about the problem, I didn't really necessarily write all these equations. I just kind of thought about, okay, these are the requirements. Like, I wrote down this inequality, but I didn't necessarily like write out all of this stuff. But just kind of from here, you know that xi is in a certain range, and then from this rule, you know that xi is in a certain range, and you're intersecting ranges to get a smaller range, and so on. And so that's basically the idea, and we just implement that here. Yeah, nice. Arya, Manex. Yeah. Half open ranges are definitely nice. And yeah, Darth Shader, exactly. Basically, they're easier to deal with. You don't have to worry as much about off by ones. Maybe the only case where it's a little weird is like this type of thing, where if you want to include h0, you have to do h0 plus 1. But it's not really a big deal. It also makes sense because like the length is 1, right? We're including one thing. Divide and conquer for C. So I don't really see a good way that divide and conquer would work here, because divide and conquer is helpful when like you can cut the problem into two halves, and then you can solve like the parts crossing the two halves better. But here, like going straight into the middle of the fence seems like a hard thing to do. In general, it seems easier here because we have these requirements of first and last. we kind of know more about the first and last than about the middle. And so it's easier to start with one of those and then go across. Yeah. Okay, let's talk about problem D then. The idea is really unobvious for C. Yeah, so basically the way that I would think about getting to it is just taking these apart and like writing observations and trying to combine those observations, kind of the way I did here, where, yeah, you just kind of take these, combine them together, and then you realize that we're intersecting ranges, so there's still ranges. Wasn't the fourth problem easier than the third one? So, and D and C should be swapped. So I actually thought D was pretty hard. I'm surprised so many people got it. Like 2,000 people got it. But it seems like kind of a tricky construction to me. So yeah. Okay, so problem D. So we have an array A1 through AN where AI equals I. So the array is just 1, 2, all the way up to N. And we have an operation where, well, it's called a step where we can take two indices x and y, and then we can convert ax to the ceiling of ax divided by ay. And we just want to make A consist of n minus 1 ones and then a single 2. And we want to do this in no more than n plus 5 steps. And just figure out how to do that. We don't have to minimize the number of steps. We just have to do it within this number. And yeah, basically we're just given n in the input. It's pretty convenient that they don't even have to give us the array. And then, yeah, we'll just output the number of operations and then just output the pairs x and y. Okay, so for this problem, the first immediate thing that I thought of was, okay, so we want to make a lot of ones, right? So we have this array, it's kind of like 1, 2, 3, 4, 5. And then if we pick a number that is, and if we pick ax and ax is smaller than ay or the same, then we'll just immediately make a 1, right? Because, for example, ceiling of 3 divided by 5 is going to be 1. And so we can just, like, let's say we have like an even bigger array. We could just take everything like 7 divided by 8 and get 1. We could take 6 and then divide by 8 and then get 1 and so on. And we could just make all these ones and then we just leave this 2 and we have a 1 here. So I thought the problem was super easy, but then we had this issue where, oh, what do we do with this last number, right? This 8. We kind of just end up stuck with this 8. And well, we noticed, okay, we have a 2, so we could divide 8 by 2 over and over. So we could get 4, and we could get 2, and we can get 1, right? And so we could do that, and we end up with the result we want. The problem is that then we're using log n steps at the end to get from n down to 1, right? Because if we divide n by 2 repeatedly until we get down to 1, that's log n steps. And yeah, in particular, n plus log n is going to be too much here because it's going to be something like, 200,000 and then 18. And then maybe, we save these two. So maybe it's like -2 or -3 or something. But that's still too much. That's a lot more than, that's like n plus 16-ish, so it's a lot more than 5. So instead, what we want to do here is, we have this sequence of numbers, and we can kind of just, we can think about, okay, how do we make the 8 smaller along the way? So one thing we could definitely do is we could divide 8 by 7, and then we will get 2. But now we're in a weird situation because we have this 2. If we kind of did that for the 7 and the 6, we would just have a lot of 2s, and that wouldn't be great. So basically a really good thing to do in terms of the number of operations would be to divide it by square root n. So let's say we just did the 7, the 6, the 5, the 4, and then finally we took this 3 and we divided 8 by 3, and then ceiling of 8 divided by 3 is going to be 3. So now we can convert n to or the last element to a 3, right? And then we can kind of keep going. So maybe a bigger example will be more helpful here. Yeah, basically the idea is like, take 15 divided by 16, 14 divided by 16, all the way down to 5 divided by 16. We'll end up with a bunch of 1s here. And now we take the 16 and then we divide it by 4, and we get a 4, right? And the key thing is this 4 is still at least as big as everything here. So now we can continue down, we can take the 4 divided by our n number, get a 1. We can take 3 divided by our last number, get a 1. And then now we've reached 2 is equal to square root of 4 again. So we divide it 4 by 2, and then we divide just 2 by 2 to finish, right? Yeah, so the main idea is basically we have this 1, 2, 3 up to n. We convert everything. We convert everything in here to become 1, 1, 1 all the way there. Then we take n and divide it by, I guess I'll do this. We take n divided by square root of n, and we get about square root of n. Or maybe it's either square root of n or like square root of n plus 1, right? And then we just keep going down again. And so we're gonna convert n to become square root of n, and then it'll become square root of n, and then square root of n, right? And so on. Until finally we reach all the way down to this 2, and then we'll be good. And so now the question is like, how many steps does that take? And I mean, we can just take the max number here, 2e5, right? If we have 2e5, we can take square root 2e5. That's about 400. We can take square root of that. It's 21. Square root again. So 3 square roots now. We're at about 4 or 5. Fourth square root, we're at about 2. And then, now a 5th square root, we're below 2. So yeah, basically 5 square roots will get us down to 2 for sure, because we're doing the ceiling division each time. And so basically this will be like n plus 5, but then keep in mind we don't have to do anything for these first 2 elements, so it's actually like kind of more like n plus 3-ish, and so that's fine. In actuality, in general, this is n plus log n minus 2. Hydrate. And that's kind of cool, right? We don't see log n too often. The reason it's log n is because if we say n equals 2 to the k, then square root of n is equal to 2 to the k over 2. And so actually it's log k, right? The number of times we need to repeat the square root. And so log k is equal to log n. Cornfield chaser. So how do you do it after you solve 8? Yeah, I saw also a couple people in chat mention they just use like, I think people said they use like 2, 4, 16, 256, and then 65, 536. And yeah, this is kind of the same idea. Instead of like square root of n, you're just starting from 2 and then repeatedly squaring it, right? And so you can use these as cutoffs as well, and that would also work. That would get you log n as well. Yeah, so I guess, maybe if you think about it this way, it's a little easier, because then you can just think about like these powers of 2 and so on, and that this sequence has length like 5 or whatever, so it feels more obvious that it fits, as opposed to like, oh, how many repeated square roots can we do? Well, it's kind of hard to tell. So yeah, I guess that makes sense. But yeah, I still thought this problem was a tough one. So, but a lot of people got it. So that's pretty cool. Yeah. And so, yeah, maybe this is like an easier way to think about it. Just think about like, oh, when you hit, you know, one of these, well, actually, what do you do starting from 2e5? I guess do you only divide it when you hit 256? So maybe you don't actually include this. So when you reach 256, you divide n by that, and then like, you know, 2e5 divided by 256 is 718, and then 718 divided by 16 divided by 4 divided by 2. Okay, and then you can just like do a couple of divisions by 2 to finish. I guess that makes sense. Oh, cornfield chaser. So cornfield chaser is saying, one, two, 1, 1, 1, 1, 1, 8, and then 1, 1, 1, 1, n. So we used n to reduce all of these to ones. We used 8 or n to reduce all of these, and then use 8 to reduce n and use 2 to reduce 8. So yours is still n plus log n then, right? It's just like a better constant factor on that. So did that actually work? And so log 8 of, what is log 8 of 2e5? I'm surprised that worked if it did. That seems like it's pushing it a bit. Atin N1 says you can use 64 instead of 8. So the problem with like trying to make this number bigger is then if n is like, well, oh wait. Yeah, but then you have to use 2 to reduce 64, so you have to use a lot of 2s to reduce the 64 to a 1. Yeah, basically this is kind of like a worse version of the above solution where like, yeah, I guess the above solution is like this, right? 16, 256, and then n, right? And so now we use 256 to reduce n. We use 16 to reduce 256. We use 4 to reduce 16, and so on. And so all of these special numbers take like one extra step to reduce. Maybe n takes 3 steps. And so that's why we just get one extra op for each of these numbers. Here, 4, 16, 256, and n. Now people are asking Codefield Chaser for CF handle. Are you guys going to try to go hack them? Or hack him? Yeah, maybe we can, let's see. How do we find a specific person? I guess you just got to go to profile. Oh, but you didn't submit problem D. Or am I missing it? Oh, this is a post contest. This is a practice submission. Okay, I see. Yeah. Okay, you guys should totally go hack him. You won't even cost him points. So yeah. I'm kind of surprised this passed pretest then. Like, doesn't it? Couldn't you just give it 2e5? Isn't that good enough? I don't know. Anyway, maybe you guys can figure it out. Am I going to take part in Goodbye? I'm not sure yet. We'll see. Yeah, I'm not sure right now yet. Genius asks, I don't even know what CF hacking is. So CF hacking is basically, well, I'm assuming you know what Codeforces is. And then hacking is basically, you can go into someone's submission, you can read their code, you can be like, okay, I think this is wrong, and you can hack it. And just enter like your test case. Okay, so I don't know, just for fun, we'll let's try some. That's not one, that's 2 test cases. So I guess I can't go quite that big. I can go something like that. Yeah. All right, let's just try, why not? Unsuccessful. Okay, yeah, you guys might have to figure out something else here. Yeah, I guess it did pass pre-test, so that is saying something. Anyway, maybe someone in chat will figure out how to hack it. Yeah, so basically you try to Shadow Crypto said you destroy others' code. Yeah, basically you try to you read their code and you're trying to find a test case that their solution won't get correct, and then you submit that, and the server will run their submission on that test case and tell you whether or not you're successful. If you're successful, it means that you found a test case that breaks their code, and so then they lose their accepted, and you, well, depending on the contest, in educational rounds it doesn't count. I guess I have a -1 now. It doesn't count to your final score, but in other rounds it can give you a couple points and like bump you up a bit. Yeah, the pretest should cover this one pretty strongly because you just input n. Yeah, exactly. So like it's not even like you can input a weird array that they might not have covered. It seems kind of hard to it seems a little hard to pass pretest on this problem and then fail sys-test unless you did something weird where like certain values of n are bad for your submission. Oh, does it affect the tiebreaker? No, I'm still 2. Yeah, we're just tied. Earlier we had SS Urinar asking for people to hack hack them. Oh, I realized, let's see, we went over all this code. Yeah, okay, we didn't go over the code for D though. Yeah, so the code basically, I just read an n, I have an ops array, just make this add op function that does pushback xy. And then I set up this loop, start with what's my big value, it starts with n, and then what's the thing that I'm converting to 1, which starts with n-1. And so while the current value is bigger than 2, we just do a little loop to find out. This is basically a loop to compute square root x, I guess. And we just make sure that ceiling division of big divided by x is greater than or equal to x. That way we make sure that big is always the biggest number. So big is basically the value of an. And we want to make sure big is always the biggest number in the array. If it's tied, that's okay, but it can't be smaller than another value. And so we decrease x until ceil div is greater than or equal to x. And then we just loop current down to x and add an op to divide current by n, which makes it 1, and then go down. And then we divide an, which is big, by the current index. And so that's the square root thing. And then we just actually convert our big value by actually dividing it. We assert it's still at least as big. Again, biggest element. Oh, and then I got a wrong submit, unfortunately, because just a pretty silly bug. Here I did add up with big instead of n. I should be doing n because n is the index. It's an. Big is the value. And so I guess the sample doesn't have n big enough to actually make that be a problem. Yeah, because square root of 4 is already 2. So we only do like 1 loop iteration here. Yeah, and then finally, yeah, assert current equals 2, because that's the value we should have hit. And then just while big is not 1, we just keep dividing it by 2. And then print everything. And then at the end, I just added this assert. Just assert that the op size is at most n plus 5. And so that way, like, I can test it myself. I can just do like this. And it did pass the assert. I can also use head to just get the first couple lines of output. And so I see that I used n plus 3. Do I submit my code if I come up with an algorithm, but I haven't proven it yet? Yeah, I've definitely submitted code before I've proven it before. I think there are times when you can be pretty sure that an idea is correct, but not have the exact proof. Yeah, basically you can know that, like, okay, you can feel like, oh, I'm pretty sure this is correct. I don't have an exact proof, but it feels like this is the right thing to do. And you'll just submit that, and then you can get kind of the proof by AC. It works better when you actually get AC than when you only like pass, some subset of the test. But anyway, yeah, I definitely have done that. How do you improve your math skills? Yeah, basically you just, it's the same way you improve anything else. You just work on different problems, you practice it, you think about it more, and then definitely like read, what other people who are better at that problem said about the problem or how they thought about it, ask other people and so on. What is dbrun? So dbrun is just the script that I have that basically compiles the code in debug mode and then runs it. And so what debug mode means is basically, what's an example? If something, bad happens in the code, for example, let's say, yeah, this is a good example. Let's say let's say I overflow, right? So this is like about 1e9 plus 2e9, which is too big for int. I guess I have to give it a test case. Oh wait, I can't give it 1. Yeah, then it will give me, like, as it's running, it will give me errors. So for example, this one is a good message that tells me like what exactly is happening. Gotta hydrate. And yeah, these are really nice because actually I'm not sure if I'll run it like in optimized mode. Yeah, it didn't catch that. It just printed out a negative number. So this is a nicer error to have when you're like testing locally. It'll also catch things like indexing out of bounds and so on. The flags, I have a lot of flags. These are the flags that I use. Yeah, I just kind of accumulated these over time from like different sources and people telling me that they use this flag or that flag. Paste here, please. Okay, let me see. Maybe via gist. Yeah, let me see. I think that makes sense. All right, I'll just grab this. Okay, almost ready. Okay, here's a link. So these are all the flags that I use when debugging. All of the all the ones that start with W are different warnings. There's like F sanitize, which forces different types of sanitizing. For example, address sanitization, which checks for out of bounds and things like that. Oh, there's also -D. -D just defines a certain flag, so that's why I can do, for example, here, I do if not defined nil debug, then cn.tie null pointer. The reason for that is so that way if I'm trying to test manually and I want to give it test cases, it will actually print out things along the way. But if I'm like running it in speed mode where it does cn.tie, then I won't get anything until I give it the entire input, because it's not flushing the output anymore. People asked about progmas. So I don't use progmas by default. So you can see I don't have anything here. Yeah, I definitely wouldn't just keep them by default. Sometimes they make your code slower actually. It's better to understand when they help. So in particular, there's fast, unroll loops, AVX, things like that. They generally help when you're doing really simple loop operations or things that are a bit easier for the CPU to parallelize. One good example is bit sets. Bit sets can definitely be sped up with, I think AVX in particular is really important for bit sets. But yeah, that's kind of a more obscure topic. Okay, it sounds like a couple people want to hear about problem E. So yeah, we can totally go for that. All right, so problem E, we have two strings A and B. They both have the same length, and we call them a bit similar. This is like a silly pun, but anyway. If they have the same character in some position, so there's at least one index I and one to k, where AI equals BI. Oh, how can I rewind the stream? You can check out this link, and the video of the current stream is there, so you can replay anything if you missed an earlier problem, for example. Okay, so a bit similar means there's at least one position where AI equals BI. And now we're given a string of length n. It has zeros and ones, so it's binary. And we're given an integer k. This is just definition of a substring. And then we're calling a binary string t of length k beautiful if it's a bit similar to all substrings of s that have length exactly k. So it's a bit similar to s1 through k, s2 through k plus 1, and then all the way to sn minus k plus 1 through n. Wait, two hydrates, okay. Yeah, crow, yeah. That's surprising. There should be a cooldown. Yeah, that's weird. Okay, anyway, we're trying to find the lexicographically smallest string that is beautiful. So it is a bit similar to all of the substrings of length k. Or we should have to report that no such string exists. Then they define lexicographically. Yeah, basically you just compare index by index and you find the first mismatch, and then the smaller one is the smaller string. Okay, so yeah, anyway, we're given n and k. N and k are up to 10 to the 6, so quite big. We get the string s, and then we want to figure it out. So for this problem, or for this sample, the answer is yes, and it's 1, 1. The reason is 0, 0 isn't good because it doesn't, it's not a bit similar with this one. 0, 1 is not good because it's not similar with this one. 1, 0 is not good because it's not similar with this one, right? But 1, 1 is good because it matches this, it matches this, and it matches this. Every substring here of length 2 has at least 1, 1. Okay, so yeah, basically for this problem, first I just started thinking about, okay, what does a bit similar really mean? Well, a bit similar it's actually harder if these are like A, B, C, D, so on strings than if they're binary strings. For a bit similar in binary, it's actually easier to think about the opposite. When are two strings not a bit similar? And the only way they can be not is if they're exact opposites. So for example, the only string that's not a bit similar with this string is exactly the opposite string, right? Anything else, if it's not exactly this, right? If it has any difference, it will be a bit similar because this character matches. So actually really what's happening is every substring of length k in S just means that there's one exact string that's not allowed. So that's actually a lot easier to deal with than this kind of matching thing that we're thinking about. Okay, so it's better actually to take S and just flip the entire string. So let's take this sample. Let's just flip the entire string. So 0 to 1 and 1 to 0. And now, what was k? K was 3. Now, we're just taking every length 3 substring, and all of these substrings are not allowed. Right? And so now we want to know, okay, what's the smallest length 3 substring that is allowed? So 0, 0, 0 is no good. 0, 0, 1 is no good. But 0, 1, 0 is okay. So that is the answer for this test case. Yeah, and then they have this example. In this example, every different length 3 substring appears. So none of them are good, so the answer is no. So yeah, so that's basically what we're trying to figure out here. And yeah, so basically if k is like 5, for example, we basically want to see if this works, we want to see if this works, then see if this works, then see if this works, and so on, right? And so these are just like binary numbers, right? Just 0, 1, 2, 3, and so on. And we just want to know the smallest binary number that doesn't appear as a substring of flipped S. So actually we can just go and find all of the substrings, length k substrings of S, and find them as binary numbers, and then write them as not allowed, right? And yeah, so Shahraz has a good point. So what if k is big? Yeah, so if k is big, then these numbers, like let's say k is like 1,000, right? Then like a random string looks like this, right? And this is some like huge number, and this string is not allowed, or this number is not allowed, right? Well, we can actually ignore this now because basically the number of substrings of length k is, what is it? It's n minus k plus 1. So anyway, in particular, it's like less than or equal to n, right? There can only be n not allowed numbers. So if we think about 0, 1, all the way up to n, one of these numbers will be allowed, right? Because we can only cancel out n numbers. So if a number is really, really huge, we can actually just ignore it. Meaning if a number is much bigger than n, we can just ignore it. So now for the implementation, yeah, we just want to find the value of all the substrings of length k, and then mark them as bad, and then find the first not bad value. Oh, people are asking for the link. Oops. Where is, no, I'm not trying to do that. Okay. I have way too many of these. Okay. All right, so here's just a general link to the contest. And yeah, you can find all the problems there. All right, and yeah, so basically for implementation, Oh, to my solutions, you can just like just go here and find all my solutions. Oh, the explanation. Yeah. Then go to the videos. Okay, so Shahraz, yeah. So we can brute force, yeah. And then we need to. The thing is, we can't do n times k to compute all the values. That would be no good because that's just too slow. But we can do a couple different things. A couple different options, rather. So the first option is we can do something just like string hashing, where we kind of build it from left to right, and we just handle that. And then since we're only doing like binary numbers, it's actually, we can just let it overflow and it works perfectly fine. The other thing we can do is we can actually say that, okay, so if we have a really long string, right? You know, if it has a, kind of like similar to the above, if it has any one that's not in the last, 20 characters, then it's much bigger than n based on what we said here, right? So if it has a 1 in anything but the last 20 characters, then we can just ignore it. So the only strings that we allow are strings that are like just a bunch of zeros, and then the last 20 characters have ones. And then in that case, we can evaluate the number just by going through the last 20 characters. So a couple different options there. And basically for my implementation, what I did is read in n and k and s and all that, flip everything. And I just recorded the locations of all the ones. And then this is I have a bool array for which things are seen. And then I just go left to right. This is my binary value. As you go left to right, just multiply by 2, add the current value. And this is a key thing here. We want to remove the higher bits and only keep the last k bits, right? And then here I just check if k is less than 32 and do that, because if k is 32 or higher, this doesn't actually really work. But if k is bigger than 32, then we're fine anyway, because we're just keeping the last 32 bits, which is more than the 20 that we need. And then finally, yeah, if we have a value, so we're just going to go through and check. We're going to go through the locations and check. Okay, is the first location, we find the first location that is at least our start. Start is the last thing minus k minus 1. We find the first location that's at least our start. If either it doesn't exist or it's at least I minus log, meaning only the last 20-ish, I think here I did like 21, 22 positions have ones, then we can use the value. And then we also check, here I just check if value is at most n, because I don't want to go out of bounds for my array. And then there's one more thing to handle, which is we have a limit of n, but we also have a limit of 2 to the power of k, because, I mean, obviously we can't get a number that is, or get a string that is bigger than 2 to the k. And yeah, so we just loop up our bool array and find the first value that was not seen, which means it's not bad, so it's usable. If it's too big, we print no, otherwise we just print yes, and we just print the appropriate bit of the answer. This is just another check to make sure, because I think shifting by 32 or more is undefined, so we just want to avoid that. Yeah, so overall, pretty simple solution. The key thing is to think about the idea of what does a bit similar really mean, and realize, oh, it's actually It's actually like telling you more about the opposite, like the flip of the string, than the string itself. I'm Mamad79. I'm trying to hack someone's code, but it keeps saying invalid input. Yeah, that means your test case is wrong. You should check double check what the problem statement says. And I think if you click on verdict, like for me, if I click on this, it will have the validator and checker output. So you can look at that. It'll probably tell you exactly what's wrong with your test case. Coffee Tail says, sorry, I didn't get why you only have to check 20 of them. So okay, so backing up a little bit, basically we're converting all of the substrings of length k into a binary number, right? And this is after we flipped s. So we flip s, we take all the substrings of length k, convert them all into binary numbers, and then find the smallest binary number that's missing from these. And the number of substrings of length k is n minus k plus 1, which is less than or equal to n. So there can be only n values that are bad, right? And so then if you have a list 0, 1, all the way up to n, at least one of these values is good. So we only have to care about substrings who have a binary value that is up to n. And since n is up to 1e6, then we only have to care about binary values that only have ones in the last 20 bits. Because if you have a 1 anywhere beyond the last 20 bits, then you'll be more than n. And so that's why I keep saying this like 20, because 20 is just log of 10 to the 6th here. Okay, awesome. Yeah, I got all these hydrates, so I'm gonna need to do a quick restroom break, and I will be back. I guess I'll just yeah, I guess you guys got what you wanted, but yeah, I'll run a quick ad break in that case, because that way fewer people will get pre-roll ads when they first show up. So be right back. Oh yeah, Crow, I'm working on the emits, so we should have something soon. Yeah, I'm already too hydrated. It's good. It's better than being dehydrated. Let me see. Someone told me I'm getting too many following messages in the chat box. Let me see if I can adjust that. Give me 1 minute. Okay, yeah, I'll just hide the chat box here. Okay. Crow, you said I didn't know you could lose rating in educational contests. Yeah, these are definitely rated. Wait, Crow, what is your account on Codeforces? I don't think I've seen your actual profile. Oh, this is your first contest. Oh, nice. That's awesome. Wait, you took away the O? It was taken. Oh, wow. That'd be nice. That's awesome. Cool to see you competing. Okay, so let's see. What else do we want to do? We have problem F. Yeah, I guess we can go for problem F. Oh, we did have a couple questions here that I might have missed. Yeah, it only counts if you're below 2100 because it's Div 2. Are problems in educational rounds easier than the regular rounds? So I actually think the educational rounds are harder than an average Div 2. For example, there was the last one, I think it was 100. There was a problem that was only solved by something like 4 or 5 people in the round, and maybe 4, and the problem rating ended up being, it was this one, Max Kirk said the problem rating ended up being 3100. And it's okay, yeah, this isn't like normal for an educational round, but like often the hardest problem is somewhere between like 2700 and like, yeah, 3100, something like that. Which is, I'd say, a little bit harder than the average Div 2. Yeah, and like I didn't get it. I had the wrong answer in test 57. But yeah, I think usual Div 2s are like, especially Div 1 plus Div 2s, these are much easier usually. And then kind of a standalone Div 2 round is also usually, for example, this problem, yeah, 2700. So this is definitely easier than like that educational round. Anyway, it's close. I would say the educational rounds are slightly harder. The Codeforces problem statements are essays. Yeah, they're definitely sometimes on the longer side. Oh, hydrate. General way to approach a problem in contest, and then how to train key observation abilities. So that little points to practice skill. Yeah. These are hard things to do. In general, it's good to kind of, for example, for this problem, it's good to like take the problem statement, think about what's like the key thing going on. The key thing is like, what does this a bit similar mean, right? And just, try some examples. For example, if you just went through this thought process and you're like, oh, which strings are good? Like, oh, okay, any string like this would be good. Most strings you try are good, right? So you try to find one that's bad, and then you realize, oh, this one's bad. And then you realize, oh, this is the only string that's bad compared to this. Even being one off from this string is still good. That's funny. I got my lunch reminder. But yeah, basically only one string is bad for any string. And then if you know that, then the problem becomes a lot easier because basically every substring of this string gives you one bad string. And so we're just trying to avoid all of those. How did I set up this Streamlabs bot? Yeah, so this is just, if you just search Streamlabs, you'll find a couple of different options that they have here. Asking about this part. Oh, this part, yeah, this is just, so this is just find the first one starting at start or later. And then we just need to make sure, like this is because the value is only holding 32 bits. We want to make sure it's not much bigger than that because we just overflowed and forgot about those bits. So this is just how we make sure we didn't actually overflow. We make sure the first one is late enough. It's in the last 20-ish bits, and then we're good. Yeah, scanner isn't recommended, I believe. You should use buffer reader. Dark Tiger, you can check out, for B, you can check out this video's link. It has the current stream, so you can find all of the earlier problems. Practicing math skills. I mean, I think CF is pretty good. It's just that if you want to focus on practicing math skills, like you should take a problem that involves some math insights and just work through it more yourself, right? And then work through different, variations of that and think about it more. It's kind of like, it's up to you how much you want to dig into the math, right? I do think @coder has like more mathy problems as well. Although it's like a certain type of math, it's a lot of combinatorics and so on, and not as much other stuff. Project Euler is definitely math. It's a lot of number theory, I believe. So different options. Math forces. I actually haven't seen this before. Is this a... Oh, I see. It's like a real website with math problems, I guess. How do they judge you? Like, how do they judge your proof? Because the whole point of programming contests is you get automatically judged, but no one can judge your proof automatically. Yeah, I've never seen this site before, but it's a funny name. I wonder how hard it was to get the domain. All right, well, we do still have problem F, so I do want to go into that. So yeah, let's go for that. For pupil specialist, I don't have anything like specific for that range. It's just the same general thought process I've been describing of just like practicing and so on. Okay, so this is actually pretty funny. This is kind of, Crow, you were mentioning earlier that the statements are so long. They at least dropped part of their statement here. But anyway, so you have a chain defined as either a single vertex, which is length 1, or length x, which is a chain of length x minus 1 connected to an extra vertex at the end. And you have n chains. The lengths are L1, L2 through Ln. And you want to build a tree using these chains. So every vertex of the tree is either white or black, so everything has a color. The tree starts with one white root vertex. All of the chains start with all white vertices. And then what you can do to make the tree is you can take a chain, you can connect any of its vertices to any white vertex of the tree. You'll add an edge that way. Then the chain becomes part of the tree. And then both endpoints of the edge become black. So basically the vertex in the chain that you connected and the white vertex of the tree that you connected both become black. And then each chain can be used no more than once, but some chains can be left unused. So you take some subset of these chains and you connect them in some order and then you end up with a tree. So just defining distance, and then if there are at least k white vertices in the tree, then the value of the tree is the distance between the root and the kth closest white vertex. And you want to know what's the minimum value of the tree you can obtain. So it's kind of like, if you can get at least k white vertices, what's like the closest you can get that to be, the kth vertex. If there's no way to build a tree with at least k white vertices, then print -1. Actron, please don't spam over and over, but you can check out the videos here, and this will give you the current stream as well, so you can watch a replay. And yeah, I do upload to YouTube. It will be a day later than Twitch, so you can check that out too. Let's see. Oh, sugar and wine. Yeah, so I have a dual monitor setup, so it's hard for me to screencast both. Like, I don't know how to do that, but if you have suggestions, you can let me know. Okay, so yeah, so here basically we get n and k. N is up to 2e5, k is up to 10 to the 9th, so k is quite big. And then you get the lengths. Lengths are between 3 and 2e5, so 2 times 10 to the 5th. So the sum of all the lengths is quite big as well. Yeah, so we need to make sure we don't do anything that's too slow relative to k or the lengths. We just print the minimum value of the tree, or -1, it's not possible. Okay, so first of all, when I get something like this, I like to think about, okay, is there an easy way to tell if it's -1 or not? So let's just say we want to know if we can build a tree with k white vertices at all, right? So then, let's see, I drew up a quick diagram. So then what's happening is, if we have a chain, let's say this chain has length 6, right? 1, 2, 3, 4, 5, 6. And then we start with a root. So initially the root was white. So we start with just this single root. And then we connect a chain, right? So we connect this length 6 chain. What exactly happens? So the vertex we connected to turns black, the vertex in our chain turns black, and then basically we get L-1 new white vertices. And so then the net change is L-2, because we lost this one rather, and we gained L-1. So the net change is L-2. The lower bound on L is 3, so every L-2 is at least 1, so it is positive. Hydrate. Can I suggest good resource for learning data structures and algorithms? I mean, yeah, I would go on Codeforces. I think that's pretty good. Things are a bit scattered, but just find different problems, find the editorials, and find submissions from people who you think are good, and just try to learn that way. Yeah, GM Mark Zuckerberg. So I decided to disable the IRL word ban for this post-contest stream, just because we're doing a lot of analysis and explaining things, and the IRL word ban is just like a lot of extra mental load, but I'll add it back for more chill streams. Okay, so yeah, so for any chain, we're gonna add L-2. So we start with one white vertex and we add L-2 per chain. So the only way it's -1 is if the max number of white vertices, which is the sum of all the L-2 plus the one initial vertex, isn't enough, is less than k, right? And so we can just do that real quick in the code, read in all the L, and then if 1 plus the sum of L-2, which is basically the sum of all the L minus 2 times n, if that's less than k, then it's -1. If that's at least k, then it's always possible, so we always have an answer. So yeah, so we figured out the -1 already, and then we're good there. And now we just want to figure out the minimum value we can obtain. So basically, for problems like these where you're trying to do the kth smallest thing or the kth largest thing, it's often really helpful to binary search, because if you binary search the distance, we just want to know, oh, is it possible to get this distance? And now, instead of doing like kth smallest thing, we're actually just counting the number of things that are up to that distance and checking that count and comparing that count to k. And so it converts this like problem with a lot of ordering and structure to just a simpler counting problem. And so in this problem, let's assume we're binary searching the end distance. So the answer obviously is between 0 and then on the lower end. And then on the high end, well, what's an upper bound? It turns out we can just use like something like, 3n, I think. In my code, I actually end up using like 1 million, which is 5 times n. And we'll get to that. We'll get to y in a bit. But yeah, so we're binary searching the answer, and we're just trying to see if we can get yes or no, can we achieve a certain distance? Okay, so there are a couple different observations we need to make in this problem. The first one is basically how should we attach a chain to the tree? Like which vertex should we pick? And you can just try this out on paper, but basically you always want to pick the most center, the most middle vertex in the chain. And if the chain is even length, then there will be 2 that are tied. But basically, if you look at this, for example, we have a chain of length 6, and we're deciding how to attach it to a single root. If we attach it at the second vertex, we end up with this situation. And so now our depths from the root of the white vertices are 2 here, because it's 2 away. So 2, 2, 3, 4, 5. And if we attached at the center vertex instead, then basically, maybe I'll write some text here. So 2, 2, 3, 4, 5 are the depths here. And then over here, we get 2, 2, 3, 3, 4, right? This drawing program is really clunky. Okay, so yeah, 2, 2, 3, 3, 4. And so if we compare this list to this list, then this one is just better. Like everything is closer or the same compared to this list. And so yeah, this is always better. So basically we always want to attach using the middle vertex. Yeah, Actron, please stop spamming. You're repeating the same message over and over. Okay, so yeah, so first observation, we'll attach at the middle vertex. And now a couple more things to think about. We want to think about what's the order we want to attach these chains in. And we want to think about where should we attach the chains. So let's think about where we should attach the chains. And I'm actually going to switch to, okay, I'm actually going to switch to Jamboard. So I guess I'll save this somewhere. Can I just save it to the desktop? All right. Okay, cool. Oh, whoops. All right, here we go. Okay, so let's see. Yeah, let's think about where to attach these chains. So let's say we have one chain set up already. Okay, and now got like a bunch of lines. And then what's going on here? This one's black. This one's also black. All right, horrible drawing, but it's fine. And now we've got another chain, let's say. So actually, I can just do this again. So another chain, and we're trying to figure out where to attach this chain. So for now, here and here are the same, and here are the same, but should we go at this depth 2 or depth 3, right? Depth 2 seems like it could be better because then all of the nodes from this chain will be closer to the root. Depth 3, the benefit there is that we keep this depth 2 instead of because when we attach to depth 2, we clobber the depth 2. Okay, so now we're thinking about this, and basically let's remember that we're thinking about binary search. So we're trying to get the max count of nodes at a certain distance. And in that case, adding the chain is only useful if, for example, if we draw a line like this, basically we'll end up clobbering this node. This will be black, right? And then all of the nodes here will be at this depth plus 2 or greater. So adding this chain can only be useful if depth plus 2 is still a valid depth within the distance. And if it is, then it doesn't actually matter whether we attach to here or attach to here in terms of like losing a node, for example, from our original tree. In either case, we'll lose a node. And if we go too far down, right? If we go so far down that, right, okay, if we go so far down and we attach this one that none of the nodes in our chain are close enough, then there's no point attaching the chain at all. So basically, from this reasoning, we can realize, when we attach the next chain, we can just always attach it at the closest node to the root. And well, this kind of combines with another observation, which is the observation on what is the order that we should attach in. And the order we should attach in turns out to be largest to smallest. And the way to think about that is like, okay, I'm going to attach some chains closer to the root and some chains farther from the root. And how should I decide where to do that? Well, basically, essentially the larger chains have more nodes. They have depth plus 2, depth plus 3, depth plus 4, and so on. And so kind of intuitively, you want them to be closer because they give you more options later, right? If you attach a really short chain to the very top of the root, you only have a few options to extend that. Whereas if you attach a very long chain, you get a lot more options. And you can kind of draw this out and like show it in a more formal way. So maybe I'll just, I won't go like fully formal, but I'll just try to give a specific example here to make it more concrete. So let's see. Okay, I do want to make a left side and a right side. Yeah, let's say we have one chain. We have one chain of length 3, one chain of length 5. Okay. So we can consider two options. One option is to attach the 3 first and then the 5. The other option is to attach the 5 first and then the 3. So this is 3 first and then 5. So this is our chain of length 3 right here. This is our root, and then this is our chain of length 5. And then we're going to attach that here. And then the vertices that we have to paint. Wait, which of these should I use? Maybe brush? That's too light. Marker? I guess highlighter is what I want. Okay. And these are the vertices that get colored black. Okay, and so the depths we end up with here, this one is 1. This is wait, what is this? This is actually 4. 1, 2, 3, 4. Yep, 4, 5, 5. So the depths we end up here are 1, 4, 4, 5, 5. And then now we can look at the other case. The other case is we attach the 5 first and then the 3. So let's draw that out. What's the point of rotating a circle? I don't think that does anything. Okay. Cool. Oh no, I'm drawing with a highlighter. All right. Okay, and then we'll highlight these in. Okay, yep. And now if we look at our depths, we have, oh, sorry, I was wrong about this one. This one is 2. Oh, no, that's not what I want. How do I edit the old one? Yeah, okay. Sorry, it's 2, 4, 4, 5, 5. Because this is 1, 2, and this is 1, 2, 3, 4, 4, and then 5, 5. And then over here, now we have a 2, we have a 3, we have another 3, and then we have 1, 2, 3, 4, and a 4. So this one, this configuration gets us depths of, for the white vertices, of 2, 3, 3, 4, 4. Let me just double check that over there. Yeah. And so, yeah, again, we notice here that the depths here are just like strictly an improvement over the depths here, because we want to get smaller depths. And yeah, you can just kind of reason about this in general. Again, the similar logic to before, but just attaching a longer chain first and then a shorter chain afterward gives you better depths. In the same way that, in a very similar way that like attaching in the middle gives you better depths, and so on. Okay, so now we have our 3 key observations, which are, oh, I guess I should just bring this in. Okay. Yeah, 3 key observations, which are, we should always attach chains with their middle vertex. That's 1. 2 is we should always attach larger chains before smaller chains. And 3 is we should always attach chains as high as we can. Oh, we still don't know how many chains we should use, but we can just try like all of the chains from largest to smallest one by one. Okay, so now for the actual implementation. So we have the binary search first. We're trying to find the smallest distance that is still possible. That gives us at least k. And then we output that. And then for the actual possible check, yeah, we're gonna sort L from largest to smallest, and we're gonna go in that order. And basically at each point we want to find the highest white node remaining and attach our chain to that, and then track how many of the nodes are within this distance. And then if at any point our count is at least k, then we return true, right? And then if we finish, we put all the chains in and we still haven't reached a count of k, then we return false. And this count, I should make it clear, this count is the count of white nodes that are distance at most this value. Sugar and Wine asked, was it a slightly easier F? Yeah, I think it was a little bit on the easier side compared to, at least compared to last time. And yeah, we saw like, you know, there was something like 60 plus full solved on this contest. So a little, definitely an easier side educational round, but I think that's not a bad thing necessarily. I think it's good to have some like variety. Okay, and then for the implementation, yeah, we want to find the highest up white node and then attach our chain to there. So how do we find that highest up white node every time? The way I did it is I just set up a heap. The heap has pairs, and the pair represents basically every time you attach something, right? You create 2 new chains kind of hanging down. So when we attach this length 5 path, we get this chain of length 2 and then this chain of length 2, assuming we didn't attach this yet. We'll have this chain of length 2 as well. And both of them start at the depth of 2 and have a length of 2. And so we just add these 2 as like options. And so, yeah, we just have a min heap on pairs. We take the top of the heap, and the first element is the depth, the second one is the length. And then, so chain dot first is the depth that we're attaching at. And then since we essentially remove the top node, then if chain dot second is greater than 1, we re-add a new chain which starts 1 lower and it has 1 less length, right? And then the start of the new chain, right? So this depth is 2, so this would be in the heap as a 2-2 pair. And then the start of the new chains are 2 below that because there's 1 here and there's 1 here. So that's why I do +2. And then I get the 2 lengths. The lengths are just len minus 1 divided by 2 and len divided by 2, right? And if these are greater than 0, we're going to add 2 new entries to the heap. And basically, we're going to do all these operations on the heap to track the highest nodes that we can get. And then along the way, we're also going to count. So count starts as 1, right? Which is just the root vertex. And then after we attach a new chain, we lose this first node of the chain, right? So we subtract 1 if this first node is within distance. And then after that, we're adding two chains that start at chain.first plus 2. So based on that, we should be able to tell how many nodes in these new chains are within this distance. And that's just distance minus start plus 1. Min of that and left. Yeah, and then just to be careful here, we make sure start is less than equal to distance, because otherwise this will be a negative number. And then similar thing here. And so we're just adding up these counts. And yeah, again, we don't know exactly how many chains we should add, but we know the order we should add them. So we can just add the first one, check the count, add the second one, check the count, and so on. And we just go all the way through, and each time check if the count reaches k, and if it is, then we're good. Gotta hydrate. Yeah, and so that's the idea for this problem. This implementation is n log squared n because we have one log n for the heap, and we have another log n for the binary search. Oh, and then back to this bound. Yeah, the observations also tell us why the answer will always be at most some constant multiple of n. It's because in the worst case, we'll just keep attaching chains again and again to like the very top of like the previous chain. I think actually, maybe in fact, since like the lengths are at least 3. Yeah, I think since the lengths are at least 3, maybe the answer is like most log n, because every time we add a chain, we're adding like 2 new white vertices as options. So I actually think the answer might be at most log n. If that's the case, we can just we can actually optimize this to like n log n times log n by binary searching up to log n. But anyway, it's not necessary. We can also improve this to just n log n anyway by basically this heap stuff. This heap stuff just tells us the order that we're adding things in, and we're actually just repeating the same heap stuff every time. Like the distance doesn't affect the heap. It only affects the count, right? And so we can just save all the heap events in a list in advance, and then just replay through the events in O of n time instead of n log n, and that way we can get n log n overall. So yeah, so for my submission in particular, I used about half a second, which is fine. The time it's 4 seconds, but I do think there were definitely some people who got to like n log n just based on runtime. Actually, this is a lot of people passing. Like maybe, for example, we can open some of these. Oh, this is quite short actually. I'm not actually sure what this is doing. So yeah, maybe people have O of n. I'm not sure. No, there's a sort. So you need to sort. Well, you can kind of counting sort here because it's small, but anyway. Yeah, anyway, so that's my idea for f. I think with a heap it ends up being not too bad. Yeah, the other thing is you can do it with like a seg tree instead of this. Like instead of, you can actually remove the binary search by adding a seg tree. There are just like different options you can do here. Let's see. Can I solve any Codeforces problem within 24 hours? I don't know about any problem. I would say most problems, yes, but any problem is probably too much. Shukran1 asked about the lazy seg tree setup. Yeah, so the way I would do a seg tree here is just that I would still have the heap, and then it's just instead of this count setup, it would basically be like, you could update all of the counts for all of the distances with the seg tree. But I think, honestly, I think that makes the implementation uglier. So I think binary search is a nicer way to go here. Yeah, it does look like other people did this without binary search. Maybe we can read through this and like try to figure out what's going on here. But I do think, in general, on these problems where you're trying to count like the kth closest thing or the kth smallest thing in case pretty big, binary search helps make that a lot easier. Can I solve any leak code problem in 24 hours? Yeah, probably. That's probably true for that. I don't know. Maybe there's some like crazy hard leak code problem that I've never seen, but I think the hardest leak code problem is probably a lot easier than the hardest Codeforces problem. Or I would say definitely. And yeah, thanks Shahraz and Coffee Tail for the good questions in chat just throughout the stream. Okay, Actron, you're really spamming a lot. I'm going to time you out, but I mean, I think CSES, the general question is about CSES. I think CSES is a pretty good problem set for beginners, especially it starts with easier problems and you can work through like topics, which is good. I've actually done like a bunch of the later problems and then decided I didn't want to do the easier problems. But yeah, I think it's good in general. Maybe the downside is that there aren't really like editorials or like ways to see solutions if you can't figure something out. But if you have some way, if you know someone who solved the problem, then that would be better. That would be pretty good. Does competitive programming help with work like web dev, etc.? So it doesn't like, transfer like super closely, but I think there are a lot of just like more general things that show up a lot in both. Just general like things like thinking through a problem or a situation, figuring out the right approach that you want to take, planning out your solution, right? Planning out your code, writing code that's bug free, right? That's like definitely an important skill in all types of programming. Doing things like writing tests, checking your code, and things like that are all really important. Yeah, Gokul Vardhan. Yeah. You shouldn't expect to become like way better in a month. It takes a while. So I would just say keep at it. How would I prepare for ICPC? I don't think like ICPC requires preparing super differently from just regular contest stuff. I would just solve a lot of problems, learn from them, read the editorials afterward, read top competitors' solutions, see how they did it, things like that. I think ICPC in particular, one thing you can do is like prepare your library because you can bring in a lot of code. And so, yeah, but I would just, like for preparing a library, I would just solve problems. And then as you notice things coming up again and again and repeating, then I would just add that to the library rather than like trying to preemptively like add everything to your library, right? Is LeetCode getting harder or are you getting worse? I don't know. I haven't checked out some of the more recent LeetCode contests. I do know that their problem writers have been like switching around a bit. I know like Alex Weiss used to write or set the problems for LeetCode. He's on Codeforces. Oh, is that not his username? Maybe it's Alex Weiss. Yeah, he used to write the leak code or set the leak code problems. I'm not sure if he necessarily wrote them or just like put them together. But then he stopped doing that, so now it's someone else doing that. That was maybe like a year or two ago. So it's been changing around a bit. It's possible like they changed problem setters and the style changed, but I haven't checked it out in a little while. So I see. Yeah. Okay. Yeah. Well, that covers the contest. I've got a little more time, so maybe what I'll do is. Oh, so first, I do want to read through this code. Maybe we can try to figure out what's going on here. And then after that, we can do a couple more chill things. Please add change main like Andrew. Yeah, maybe I will take a couple problem requests in the chat and just like go through some of my thought process on those. And I've also been drinking a lot of water, so I actually need another restroom break. But yeah, if you have some like specific problem requests that you've been kind of thinking about, you can put them in the chat. I'll try to take a look. And yeah, I'll be back in a minute. Hydrate. Yeah, I'll consider adding change main. Yeah, I've been thinking about different things. Yeah, Crow, you can ask known DP problems. That's totally fine. Okay. I'll be back in a minute. I guess I'll run another ad break. So. Okay, let's see what we got. Do Fenwick trees, Enrique Kai asks, do Fenwick trees and I think that's union find questions appear in Div 2 contests? I've been learning those but have not had a chance to apply. Yeah, I think they definitely both show up. Both of those are like very common topics that are useful. I think it's good that you learn those. It's just, unfortunate that you haven't had a chance to use them, but I think, if you keep going, you'll definitely run into them. Okay, so let's see. So first I did want to check out this code. Let's see if we can figure out what this is doing. So this is for F. Okay, so read in all the L, sort them, reverse. So what is this? What is J? LJ, oh, LJ. Okay, sure. Oh, this is just, oh, wait. Oh, I see. Okay. This is just like a smarter implementation of what I did, where you don't need this heap because you can just keep this array A, and yeah, this is my like chain.first plus 2, same idea. So A I plus 2 plus plus, so you get one more white vertex at I plus 2, and then I plus 2 plus U minus minus. So this is kind of the tricky idea, because really you get one more vertex at I plus 2, I plus 3, I plus 4, and so on, up to I plus 2 plus U minus 1. And so what he's doing here instead is, instead of like incrementing the whole segment, which takes, linear time, obviously, you just increment the start of the segment and then decrement the end of the segment. So you're actually like tracking the delta array, where it's like AI plus 1 minus AI, or maybe AI minus A minus 1. Anyway, you've got the delta array, and then you just convert the delta array to the regular array by adding things as you go. Okay, so yeah, this is a very similar idea. It's just you can remove the heap with this array idea, and then I guess you just don't even need to. Oh, you just use the fact that, okay, yeah, you have the count of white nodes at every level, and then you just, how many nodes are at up to a certain distance, and you can just check that for K. Okay, that's pretty cool. This is a nice trick, because I did know about this trick of like increment the beginning, decrement the end, but it's pretty tricky that you can do that and then rebuild the actual array along the way as you're iterating. Like, that's something that's new, I haven't seen before. I'm a mod says still having problems hacking the problems. Fail S is invalid, test case 1. Which problem is that? I bet you're just doing something silly where like for example, if it's this, like, I bet your S doesn't have n characters, or it has something other than, like, it has a 2 or something. Yeah, you should just like, I would just read the problem again and make sure you're satisfying it. Here. A lot of E's are getting hacked. Oh, really? Let me see. I don't see any. Oh, here's some successful hacks. Oh, this one got hacked. Oh, so much template. What is this? Oh, this is like a. Oh, this is like a hash. Oh, but they use. Oh, he used rand. Okay, that's not good. Maybe he got hacked because he used rand. Does it say who hacked him? I'm not sure who that post about. Oh, it might be a while ago. Did I post in here? yeah, I have a post about why rand is bad, so you guys can check that out. Wait, what did I do? What did I do, Crow? But yeah, it's a whole post about why you shouldn't use rand. Oh, I see what you're saying. I can't even view my profile. But yeah, anyway, why you shouldn't use rand in competitive programming. It's like, it's a lot of reasons. It's just bad. So check out the post. Yeah, I see. Yeah, I don't know why you would want to use rand here though, when you can just use binary, right? It's like, I see. I think they're just trying to, oh, I see. Okay, so maybe if you have like string hashing set up, maybe an easier implementation then is just like, instead of viewing numbers as binary numbers, you can just view strings as like the strings themselves. You find the hashes of all the strings of length k, and then you just start with all zeros. You check if that's in your hash set. If it is, you bump up to like 0, 1, 0, 0, 0, 1. You check if that's in your hash set, then you bump to 0, 0, 0, 1, 0. Like you're just, then you have to like simulate incrementing binary numbers as a string, which is like, I mean, I guess that's fine, but it's just like, I would rather just use a number here in this case. Now Actron can email me. Yeah, he'll email me every day. Okay, so let me check out what problem requests we got. Okay, so I'll do Crow's request first because well, Crow is asking first, and then also Crow's a sub, so I'll do sub priority here. Let's see, making change SQL. Okay, so I'm not sure. I might just talk about the problem. I might not necessarily implement it, just so that we can get through more of them. But we can definitely take a look. Okay, so given a list of integers denominations and an integer amount, find the minimum number of coins needed to make amount. Return -1 if there's no way to make amount. Amount is up to 500,000 and is up to 10. Okay, so the answer is 3 because we use 25, 25, and 10. Here we can't make 8, so it's 9. I see, yeah, so this is like a pretty normal knapsack problem where basically we have a bunch of options and we want to find, so basically we have a bunch of options. The options add up the value to a certain amount, and then the options also have a cost. In this case, the cost of everything is 1. But you can have a more general version where you have a bunch of items. Each item has a value and it has a cost, and you want to get to a certain total value for the min cost. And then there's actually another variation you can do on this, where in one version you can use as many of the item as you want, and the other version you can only use one of the item. In this version we have the as many as you want version. Yeah, and so basically we're just going to go through and we're going to have a DP state here. It's like a knapsack state where it's like, essentially it's like DP prefix. So we're doing a prefix of denominations, and then we're doing, I'll just call it K. This equals the minimum number of coins to make K using the first prefix denominations. So I guess I'll call prefix p instead. So for example, dp, so for example, dp2 of 7 would be 3 because, I guess I'll just save this file. Because with p equals 2, we were able to use 1 and 5. And if we want to make a 7, the best is this, right? Which is 3 options. Yeah, if it was American coins, then you can just do a greedy. Like for this one, you can just use as many 25s as possible and then go down. Yeah, but then in general, you need to do this dp instead. So does that make sense why this value is this? Like what this definition is specifically. And then we're also gonna initialize the values to be, so dp00 equals 0, right? Because you can make 0 with nothing. And then dp0, anything else is gonna be infinity because you can't make anything else without coins. So we're just gonna start, so basically, yeah, the dp0 rate starts with a 0 and then a bunch of infinities. Okay, definition makes sense. Yeah, and then the key thing is just like, basically dp of p plus 1k is going to be, it's the minimum of either you don't use any of p, in which case it's dp of pk because you didn't use the pth coin at all, or you do use it, which means that it's basically we have k minus denominations p after we use 1. So if we use 1, it's going to be 1 plus dp this. And then in this case, because we can keep using it again, we're actually going to use p plus 1 here. Because we can still use more of denominations p if we want. Hey YC Light, we're just doing like chat requests for problems and going over them. Yeah, so this is an important distinction to make. If we're allowed to reuse the coin, then we use p plus 1 here because p plus 1 allows us to use that coin again. If we're not allowed to use it more than once, we're only allowed to use it once, then we would have to do this, because then in that case, we're only allowed to use the first p coins and not the pth coin. So in this case, this is what we do. Yeah, and so this is just the recurrence we make. And so we're just gonna code this by making basically an n plus 1 times amount plus 1 array. Like these are the 2 dimensions. And then we're gonna start, dp00 equals 0, dp0, anything else equals infinity. And then we just loop p, 4p, 4k, and then we just do this, basically. Oh, one other thing to note is the order that you loop k is important. So here we want to make sure we already computed p plus 1 k minus denominations p before we compute p plus 1 k. So we just do k in increasing order, and then we're good. Yeah, so that's basically the solution here. If you want to reduce the array memory, we can actually get rid of this dimension with a sliding window. The key thing is that p plus 1 only depends on p, and so by the time we're computing p plus 1, we can throw away everything except p, and that way we only keep basically 2 arrays of size amount plus 1. So it's kind of like, you have like previous dp, and then you have like, current dp. But this shouldn't be necessary here, because 10 times or 11 times 500k is only like 20 megabytes. This is the problem request, so you can read the problem here. Okay, cool. Let's check out what the other requests were. Okay, so we have this problem here. Let's see what this is. So this was requested by Hegdahl. Consider an infinite chessboard and a special knight whose move types can change given power-ups. Was this from a contest? This is from IPC 2019. I see. Wait, was this like the hardest problem from the contest, or it's like almost the hardest? I see. Okay, you sent me a really hard problem. So let's see if we can figure out what's going on here. So n is bigger than I expected it to be. I thought n would just be like 15, but it's actually 1,000. So we start on the first card, A and B are the offsets, and P is the price. You fake solved it. Is there, can I see like the scoreboard of this contest? How do I get that? How do I search this? I guess I'll just search this. Okay, so I see RC, AVP are pretty big. Yeah, I'm not sure if this will be easy enough that I can finish solving it on stream, but I can try to think about it a little bit. Wait, why does it do this? How do I get the contest itself? Oh, this is annoying. Oh, was the contest, maybe the contest wasn't run. Oh, I see. The contest wasn't run on here. Did I miss it? Oh, okay. This only had one solve, and this is. Wait, is this what team is this? 2019. Is this the team with Eknerwala and Kaysun? It might be the team with them, because they were ICPC 2019. Let me see. Yeah. This is the one. Okay, this is the team with Eknerwala and Kaysun, and this problem, they spent like almost 80 minutes doing this problem. So I don't think I'll actually have time to solve it on stream. It does seem pretty hard, and it's a lot bigger than I expected. I was trying to think about, basically the way I would think about this. Maybe I can tell you what my approach would be, which would be helpful. I would think about, like, if I have A and B, what can I do? One thing I noticed immediately is you can do an AB, and then you can do a negative AB, and that way you can get just a 0, 2B. And then same way you can get a negative 2B, 0, negative 2B, or you can get a 0, 2A, negative 2A. So you can jump by 2A or 2B in either direction, as much as you want. And then maybe there's something going here with like GCD of A and B. I'm not completely sure about that part, but for example, like if A and B are 1 and 2, you have knight moves, right? And so knight moves you can get to anywhere. Yeah, and it seems like it might have something to do with GCD of A and B. And then based on that, I would try to figure out, like, okay, starting from the first card, where can I get to? And you need to get some like combination of cards that gets you to 0, 0. And maybe if you figure out enough about like what happens with a certain combination of cards, then you can probably figure out like what the state space should look like. Either it's equivalent to A0 or AA. Yeah, so based on what I said about 2A and 2B, you can definitely move by just like GCD of 2A and 2B, because of, what's this called? It's Bezout's identity. Basically, you can combine some linear combination of A and B and get their GCD. Yeah, so I think there are a couple things like that here, but yeah, I don't think it's practical for me to like try to solve this whole problem, especially given that it took, Eknerwala and Kaysun as a team like 80 minutes to do it. And yeah, this is funny. They were just so far ahead of every other North American ICPC team that year. They kind of really should have won World Finals. I mean, like, how do you have a team with this guy and this guy, and then also the third member of their team was Injan, who Injan had a like 3100 rating at the time. And yeah, they got second, unfortunately, but still good stuff to them. And they just obliterated every other American team, I guess. But yeah, would have been nice to see them get first. Can I show problem H? Yeah, this is problem H. Oh, sorry, this is problem K. Problem H, yeah, I don't know what this is. This is probably something even more ridiculous. I see the answer here is pi. That seems kind of funny, but I see Hegel. Yeah, I did have another request. Let me check. So from Dush 1729. Okay, this will probably be the last one I'll do, and then I'll end the stream and grab some lunch. So just close out some of these. Is this another ridiculously hard problem? Oh no, this is, okay, this is round 1A, so it should be, wait, did I do this problem? Chef plane and average distance? I think I did this problem. What happened here? Okay, well their scoreboard is just totally broken. Actually, on a stream AOC speedrun at 6 EST. No, I think I'm gonna go eat food. I heard from Andrew that I think on Saturday, yeah, on Saturday he did Ad Coder Grand for 3.5 hours, then he did Code Chef for 3 hours, and then he streamed for like 5 hours, and that was just insane. I'm still not sure how he did that. Also, he had to get up at 4 a.m. for the Ad Coder because that's when Ad Coder starts at in PST. Oh, I guess I can. That's true. I guess I can restore the word ban. Okay. Yeah, it should be back now. Tips for constructive problems. Yeah, I would just say practice different constructive problems. Look for, like, maybe write down patterns that you start seeing again and again. Oh no, we already got a word ban. Okay. Okay, how am I gonna replace that word? I don't know. We'll just figure it out. Okay, so for constructive problems, often it helps to look at small examples, then take those small examples to try to combine them together to get bigger solutions. There are different options here for constructive problems. Often it does help to just think about them. I'm really close to saying the word. Think about them, then make observations about the structure, then figure out what you can do from there. Yeah, I'm replacing it with the pause. Oh, this is Code Chef Snackdown. Right, no two problems are exactly the same, but you do have different patterns that come up again and again. Oh no, I said it. You have different patterns that come up again. And then you can take those and generalize them. Oh, I said it again. Oh, it's so hard. I really hate word ban. No, I cannot pronounce that cyanide. No. Oh. How many DP patterns are there? I mean, there isn't exactly a number. It's just there's a certain set of patterns you can learn. There's a certain set of patterns you can learn. Ultimately, it's not too many different things. There's a lot in common. You'll start seeing the same patterns again. Right, 1-0 knapsack, poly knapsack, those are things. There's also counting DPs are also common. Just in general, when you can find something about the problem where only a certain part of the state actually matters, where the rest of it doesn't matter, then you can generally compress that into a DP because you can just focus on that part of the state. Okay, let's look at this. Chefland, average distance. Even the titles are trying to get me. Yeah, working on the problem as recursion is often good. You can just write a really simple recursion and try to figure out which part of the state you can focus on and which part you can throw out. Okay, so grid, n rows, m columns. Okay, Manhattan distance. Oh, is that it? Oh, no. Okay. There's an actual grid. Okay, so yeah, so the subtask, you just iterate all pairs. You have enough time. So you just print out. How do I tell? Okay, the word ban is only supposed to last 5 minutes. So let me see. Okay, we're 4 minutes in, so almost over. So okay, so this is easy. Then for the rest of it, let's see. So what did I do here? So the first thing I'm thinking is when you're thinking about Manhattan distance, you can actually do this 45-degree rotation. After you do that, you end up with Manhattan distance becoming basically max norm. No, not norm, max norm. Also known as infinity norm. Yeah, where the distance of a vector x is just the maximum xi, absolute value of xi. Okay, IRL word ban was 6 minutes ago, so we're good now. It's over. And what that means is basically the set of things within a distance d from a point is just the square around the point with kind of radius d. Or in 3-dimensional would be a cube and so on. So basically, yeah, in normal Euclidean distance, the set of things up to a certain distance d from a point is a circle. In Manhattan, it's a diamond, right? And so if you rotate it 45, you get a square. And so that's why you get this. And often the square is like easier to work with in the problem than the diamond. So if we think about that rotation, we convert everything to a grid where now we're looking for things that have a distance of a certain square. Then the problem becomes a lot easier. You can do like kind of like top left corner rectangle sums. And that way you can just compute the sum of any inner rectangle in O of 1. And that way then you can start at a point and just iterate the square out and count the number of points, the number of ones in each square. So let me see if I can find the code. Okay, I think what happened here is that Scott wrote this code because we were teaming here. Yeah, I remember we teamed for this snack down, and then ultimately we decided not to get up at 3 a.m. for the last round. But this was like the first round. Okay, it looks like this is different from what I described, but basically you can do that rotation The easiest way to do that rotation is instead of being at xy, you convert that to x plus y and x minus y. Or actually, I think this is a more proper rotation. X, Y, X. But anyway, either of the two will work. It'll give you that situation where Manhattan distance is converted to just that square distance or infinity norm. And then what it does do is it makes your grid larger. So I guess both dimensions double in size. So you'll end up with like a 600 by 600. And then you can still do it. Just pre-process all of the top left corner rectangles, find their sum, and then you can query the sum of any rectangle in O of 1. It's like the same idea as prefix sums. It's just like two-dimensional prefix sums. So it's instead of, this minus this, it's like, I guess I can draw that out to help explain that. So basically, let's go to do this. Maybe I'll pull up, I'll pull up this. So how old is my, Scott redeemed the hydrate. Scott, we're talking about you because we got a request for a problem where on CodeChef where we actually did it together as a team. And I think I had your submission here. We were looking at the code and I realized you wrote this code because you love your go-go name. How old is my profile picture? Oh, my profile picture is like from like 2016. This was Snackdown 2019. Crow hates your coding style. Anyway, yeah, okay, I was gonna draw in here. So basically, let's say we have a rectangle. Can I draw a rectangle with this? I can draw a rounded rectangle. Okay. Sure, yeah. Okay, let me actually make a new one. So we've got this rectangle. Let's say we want the sum of this rectangle. Well then, what we can do is, oh, do I have to do this again? Maybe that's not what we want. Okay, I'll just draw lines. So let's draw this line. Oh, that's a highlighter. Now we want pen. Yeah, so the sum of this rectangle here, this one, I guess I can do this. The sum of this rectangle is going to be, it's this minus this plus this. So you just take 4 of these top left rectangles, add and subtract them. It's kind of inclusion exclusion like, and then you get this inner rectangle. And so then if you just pre-compute an array that's all of the rectangles that look like this, then you can query any rectangle in O of 1. And so a square is a rectangle, obviously, so you can query a square. Yeah, they're talking about coding styles, so they're just talking about like, where was it? Like doing this instead of, I can't edit here. Why does this even have a cursor? That's kind of weird, actually. Instead of doing it on the same line. What am I doing after 2D prefix sums? So, yeah, so you basically take your input like this. You do the XY transformation, and you get a new grid that is, I guess it's n plus m by n plus m. And then you have this new rectangular grid where you're doing square distances. And now, if you just want to query how many things are a certain distance away. So now if I have this rectangle and I have a point in my rectangle, I guess I'll make a square. That's not a square. How do I do this? Why wasn't that a square? This is the square tool. I don't understand this. Okay, but anyway. Let's say this is a cell in the grid. We want to know how many things are, within a certain distance of it. Then, let's say D. Then we'll just draw this square that this square contains everything of distance up to D. And then we'll draw another square, which is everything of distance up to, D minus 1. And if we get the sum of the outer square minus the sum of the inner square, we know exactly how many things are the same, or the exact distance D from that. And so then we can just do, where was the problem? We can do this problem in cubic time, because then we can just start from every house and then iterate the distance out and count how many things are that distance. Scott's asking me questions. So I didn't do an AMA, I did a problem request stream. But favorite matchup in Melee? I don't know how many people here play Melee, but let's see. I think Marth Sheik is actually pretty nice. It's hard though. It's hard for Marth. I also think I think Marth species is just and just ducking on them is fun. Although there are too many species, it's getting boring. Favorite type of programming contest problem? I don't know. I haven't thought about these questions too much. I do like nice problems on trees. They are pretty nice. What else is nice? Yeah, sure. Let's just go with trees. Yeah, that's a good question. Cyanide. What is yours, Scott? Douche 1729. Yeah, x minus y, x plus y is to convert diamond to a square. Yeah, so for example, let's say, maybe I did too many. Yeah, so we have points in diamond formation like this. So we're gonna say this is 0, 0 here. So this is gonna be 0, 2. This is gonna be 2, 0. This is gonna be 0, -2. And then this is gonna be -2, 0. Oh, I just messed up this point. Okay, I'll put it on the left. And then what will happen is 0, 2 becomes -2, 2. Did we? Oh yeah, let's just check this out. -2, -2. 2, 0 becomes 2, 2, and then 0, -2 becomes 2, -2. Yeah, and so if you think about that, basically we took this square and then we rotated it like that. It also became bigger. So it went from like this to this. Oh, I guess I should have mirrored it the other way. So we went from this to this. But anyway, yeah. Yeah, so if you just play with some coordinates and you try out this transformation, you'll see what happens. The other cool thing is you can reverse the transformation pretty easily too. So x is just basically if you have a transformed version. I think often people do x plus y and then x minus y because that lets you do this. But x minus y, x plus y is actually a proper rotation. X plus y first gives you like a rotation and a flip. But either way works. So the point is just to convert the Manhattan diamonds into squares. Yeah, Scott's problems are definitely favorite problems are definitely combinatorics and interactive. Scott was telling me about one time he was doing, I think it was like a lockdown versus Kennedy, and then, or maybe a team lockdown, and then Scott opened the problems and there was an interactive, and he was like, "Oh, let's go, we're gonna get this," and then he just like immediately went for the interactive problem. He was like, "Oh, I'm gonna snipe Kennedy, like I'm gonna beat him to it," and then after the lockout, Kennedy said, he's like, "Oh yeah, I saw there was an interactive problem," and I was like, "Oh, Scott's pretty good at interactive, so I'm just gonna skip that problem." Oh, what is interactive? Interactive means that maybe can I find one on Codeforces? Okay, I guess none of the recent contests have one. Here's a guy. Yeah. So I think this is an example problem. So yeah, you're just trying to guess the number, and the number is going to be between 1 and 1,000,000. And what you can do is you can print. No, here you can print. You can just print a number, and it will tell you. For example, you print 8. It'll tell you the number that you want is greater than or equal to 8. You can print 20. It'll tell you the number that you want is less than 20. And so, like, instead of a normal problem where you read all the input and then you print all the output, you print something and then the server tells you something, and then you print something again, server tells you something again, and it's like a back and forth. And here, obviously, it's just a binary search, so it's just a binary search problem. There's also kind of a joke that every interactive problem is binary search, which is kind of true. Like, I think at least half of interactive problems are binary search in some way. But there are often problems that are like some kind of cool thing that's not binary search as well. So there can be different types. Scott linked to something from, seems like a long time ago. Wait. Oh, is this just, oh, this is just in, this is just a problem that you like, not an interactive problem, right? No, I didn't say every. I said that's kind of the joke. Well, I guess I said, yes, I said every, but that was a joke. That's kind of the joke that's running. It's not literally every. How to solve A? Wait, Shan to HQ. Which A are you talking about? Are you talking about the educational round? Yeah, I guess I'll just assume that they're talking about the educational round. Yeah, so you're like a few hours late, like 3 hours late actually. But we went over these problems earlier in the stream. You can check out the video link here. Yeah, I guess technically I should change the title, but I'm probably just gonna end the stream now. So thanks everyone for coming. Yeah, definitely follow if you want to hear about future streams from me. And let me see if we want to raid anybody. I don't think I see anything like super related. right now. There's this. Why is there's always this pet ducks channel that I don't really understand in science and technology. But anyway, okay, I guess we won't raid today, but what is BSIO? Oh, I see. Oh, Techie Chan asked about this problem. I guess, okay, if it's a short one, maybe we can just look at it for 2 minutes. Turn a matrix containing minimum values of all k by k submatrices. But what are the constraints? Okay, well, I guess you can do this in like, you're supposed to do this in linear. Yeah. I think the key thing here is just to try to solve the problem in 1 dimension. And then, yeah, once you can do the problem in 1 dimension, then try to bring it out to 2 dimensions. But yeah, basically this is, for here you want to use, there's like general RMQ, but you can use monotonic RMQ. I don't know if there's like a good, yeah, like this kind of idea, monotonic stack RMQ. It's actually, it's more of a queue than a stack. But anyway, yeah, you can basically get all of the, think about like just a single 1D array and trying to get all of the minimums of subarrays of size k and do that in linear time. And then you can just apply that to this problem. Oh yeah, thanks Chordfield Chaser. Yeah, there's a good tutorial on CP algorithms according to Codeforces Chaser. Ankush, please don't spam. I mean, in general, yeah, I don't have any specific tips for like div2c in particular. Just, I would just say practice in general, you know, read the editorials and so on. But anyway, I'm going to end the stream now for today. So thanks everyone for coming to check it out. Hope to see everyone again next time.